So in this video, we are going to see how to define new data types inside Haskell programs. In fact, it is common while writing programs to define new data types in order to really understand what we are working with while using some data. And since, of course, also smart contracts are some kind of programs, this will be something that we will, of course, do also while writing our contract. So let's start by looking at the most easy way to define a new data type inside Haskell, and this is done by using the type keyword, followed of course by the name of the new data type that we are defining. In this case, I am defining a data type that I'll call int list, and what type does is defining an alias for an already existing type. And in this case, I want the int list to be an alias for the list of integers, and that's it. This is a new type inside Haskell. Well, actually, not truly a new type, since from the compiler level, there is no difference at all between an int list type and a list of integers, since as said before, the type keyword allow us to define aliases for already existing types. And I can show you that there are also some built-in types in Haskell that are defined using the type keyword, and notably the string type is defined. So in fact, we can ask for info in GACI of the string type, and we'll see that this is the definition of the string type, and this string is defined with the type keyword as said before, then string of course, and then an equal telling us that string is equal to an array of chars. In fact, from the Haskell level, there is no difference between an array of chars and a string itself, and we can even ask for the type of both the expression we just used, and we see, well, of course, that the array of chars is of type of array of chars, but we can ask also for the type of the string, and we see that the type of the string is, in fact, an array of chars. So from the GAC point of view, there is absolutely no difference between something defined using the type keyword and whatever we said that this new type defined is going to be equal to. Now, before going on to see the next way that allows us to define new data types, I want to add a little important side note here. Types in Haskell can be grouped via kinds, and we can ask for kinds of a specific type, as we also saw some videos ago, by using the colon K followed by some type, and we see as an example that the kind of the simple int is just an asterisk, and you have to read this asterisk as a generic type. So we know that when encounter just this asterisk, we know that this type can have values of course, this type. And we already see also up here that also the string does have a kind, and that kind is also of a type of a single asterisk. That means that we can have direct instances of a string type, and that is true, we saw it. And since a string is equal to an array of char, we must assume that also the kind of an array of char must be a simple star, and that is true. Of course, we saw it also here. But if we ask for the kind of a simple list without any type specified, we see that we got something different, and this seems to be a function that, given a simple asterisk, meaning that given something that can already have some instances, returns an entirely new simple asterisk, meaning that we can have instances of this new type here, but we cannot really have an instance of a function that, given a kind, return a new kind. In fact, we cannot really have instances of an empty list, If we ask for the type of an empty list, we see that this type is just generic, and we see also here this A. And as we learn, usually a simple A stands for any type possible. In fact, we can ask for the kind of a list with any type possible, and we know that integers, as we saw before, are valid simple types, so are also valid inputs for this kind of type function. And we can ask now then the type of the list provided with an integer as type that substituted this a in this case. And we see that the kind of the list of integers is a simple asterisk. In fact, we provided a simple asterisk inside this function, and this function returned a new simple asterisk, which is the list of integers. And we can define kind also, as we saw before, by asking for the info of the string type. We saw that here is defined the kind also of a new type, which is in this case string. And we can do the same here. We can tell to GAC that the type in list is of kind simple asterisk. Well, of course, we need just an extension in order to do so. So when GAC encounters this line, he knows how to interpret it. And kinds are useful since, say, I define the int list to be something that given a type returns an entirely new type. Well, we would have got an error here since the alias I'm signing to int list is not of this kind, and so there might be something wrong in this definition. And in fact, when using this, we are, as said before, kind of defining a function for types where given a types, return a new types. And just like function, we can specify arguments to use into the definition of that type. And in this case, I'm changing the definition of int list to be just a list. And this list takes an any type as argument. And notice how the error here is already gone, since by providing this argument, we are getting something that given a type returns a new type. And I can use, of course, this parameter inside the type definition. And now the list as defined here is a perfect alias for the generic list. In fact, when providing an argument like so, the what we are doing is very similar to template in C++ or generics in other languages. So new types defined with the type keyword are not really exciting because of the data keyword that allows us to define also new types, but this time the types we define are entirely new from the GAC point of view. In fact, I could define a new type that I'll call my own list, and I want this type to take any type as argument. So we know that the kind of my own list is a function that given a type returns a new type, of course. And notice how to define kinds, we always have to use the type keyword. In any case, I'm using the data keyword in order to implement the definition of the my own list data type. And an important feature of the data keyword is that we can define multiple ways to construct our new type given different constructors. And we can define different constructor, well, of course, by assigning them a name, and the name must have the capital as first letter. And my own list will have a constructor that I'll call empty list, which will take no arguments, since of course it is an empty list. And then I use a pipe char in order to tell that what follows is an entirely new constructor, so a different way to create an instance of my own list. And following the real list of Haskell, I will define a constructor that I'll just call count. And these counts will take, of course, a value of whatever type this list is holding, and then recursively an instance of my own list parameterized with the same type we are holding. And that's it. That's how we can define new data types using the data keywords. And this new data type is dual to the real list of Haskell, since also the real list in Haskell is defined using the data keyword. And also this definition is of course parameterized by a generic a for any type. And in the definition, we see that there is a pipe here. So we do have two constructors. One is for the empty list, and one is for the const, which given an instance of whatever type we are holding, and an instance of the list holding the same type returns a new instance. And as we know, these constructors are actually functions inside Haskell. In fact, also our constructor here are in fact function. In fact, let me load the file in which we do have our definitions and ask for the type of the constructor of my own list right up here. And we see that this is a function that given any type and an instance of my own list with any types returns a new instance of my own list with any type. And as we know, this is very similar to the type of the built-in constructor, which given anything and a list of anything, return a new list of anything. And just like with list, when defining an entirely new type using the data keyword, it is possible since we can have multiple constructor for an instance to use pattern matching in order to define function with that type. And let me show you what do I mean. We could define as an example a function called my own list to string, which given an instance of my own list parameterized with any types returns a string. And I'm using pattern matching in the definition, where saying that when we got an instance of my own list that has been built using the empty list constructor, then we just return an empty list string. Instead, when the instance has been constructed using the const, we assign some names to the values that have been provided, and then use those names inside the definition. And of course, by reloading the file, we can test this function right up here by constructing at the moment an instance of my own list and providing it to the function, and we see that we get back the expected value. So we know that we can use pattern matching also with data types defined with the data keyword. And then last but not least, there is another keyword that allows us to define new data types, and this keyword is the new type keyword. And what the new type does is, well, of course, defining a new type, but with some constraint in the definition. In fact, we can have constructor just like we do in data definitions, but we can have only one of them. And also, this constructor must have exactly one field, no zero, no two, exactly one. But we can, of course, define the type to be parameterized so that we can use that parameter inside the type definition. And that's it. That is how you can use the new type keyword. And a legit question here would be, well, why this type definition would ever have been useful? And the fact is that using this type definition removes some overhead, also thanks to the constraint that we have in order to define such a type. And another important difference is that the instances of this type defined with the new type keyword will be totally different types rather than using the simple type keyword. In fact, these are alias, as said at the beginning of this video. Instead, these are totally different types. So in this case, list defined using the wrapped list constructor as a totally different type than just a list, as we can see here, whereas as seen before in the video, using just the type would have make no difference. So that's why you may want sometime to use also the new type keyword. So in this video, we saw the three main ways to construct new data types inside Haskell. We also had our first introduction to kinds, which are kind of types for types if you want. We saw how to use pattern matching also with our own types. And in the next video, we are going to see some of the data types that are already defined inside the Haskell language. So if you learned something from this video, consider to subscribe to the channel. Also, if you really want to support the creation of this content, you can go in the description below and check for the link that allows you to delegate your ADA to Harmonic pool and earn interest on top of supporting the creation of this content. In any case, I want to thank you for your time. Remember to stay decentralized, and I will see you in another video. Bye bye.